All right, it's 4 o'clock on October 2nd, and I'm going to go ahead and start this session for today. As a reminder, our sessions are every Thursday from 4 to 6 p.m., and I will be here to run through some of the background information of the lab and discuss some of the key points of the lab. Uh, this week we are doing a lab on free fall. It's an expansion on the idea of acceleration and expanding to this specific case of an object that is falling towards the Earth. And we'll see some interesting stuff when it comes to free fall. Okay, let's go ahead and share my screen. All right, and we are looking right now at a PowerPoint for free fall motion. Now, we are still focusing on this idea of graphing motion. We like to graph motion because when we have a graph of motion, we're able to make predictions about that motion. That becomes a very powerful thing to be able to do. And in this idea of graphing motion, we are going to continue on with the idea of position versus time graph and velocity versus time graph. And all of that comes from all of those types of graphs look different depending on the type of motion. So going through a little bit of a refresher to begin with, this idea of ticker tapes, right? We've talked about this every week for the last couple of weeks, and we can use ticker tape to identify objects that are, let me get out my pen. We can identify ticker tape motion as being constant speed, and that's the case where the distance between any two neighboring dots are constant. When the distance is constant, that means that we are covering the same distance in the same amount of time. That is an indication of constant velocity. We're not speeding up, we're not slowing down. If we were speeding up, then the dots would start off close together and they would spread out as we continue through our motion. This is an indication that at the end, we are covering more distance per unit time than we were at the beginning. And the larger the difference between the separations of beginning and end, the larger the change, the more acceleration we say that we have. So that bottom count is a lot of acceleration. So acceleration tells us about changing speed. But acceleration is what we call a vector quantity. And a vector quantity is just a fancy way to say it has directionality. And last week we looked at this same graph of velocity and acceleration and saw that acceleration and velocity both have directions. They both point in a direction, right? If we look at our velocity vector as it goes throughout this motion, the faster the little red ball moves, the larger the arrow becomes, indicating a larger velocity. It's moving faster. And that velocity is always in the direction that the object is traveling in. The acceleration, however, might be differing in direction depending on which part we're looking at. At the beginning, where the acceleration and the velocity are pointed in the same direction, we see that the object is speeding up. So right here, we see the object speeding up. But once it gets to the point where the velocity and acceleration point in opposite directions, we have the object slowing down. And this is a good rule of thumb to have, that when an object is slowing down, the directions oppose each other. When the object is speeding up, that means the direction of velocity and acceleration must be in line. So you have this idea of directionality, and that's going to be very important for today, for this idea of free fall, directionality. All right, well, once you have this idea, okay, acceleration means changing velocity. And depending on how our acceleration and velocity align, we might have speeding up, we might have slowing down. But how does this appear on our familiar graphs? Well, when you have an object such as this little red car that is speeding up, how do we know it's speeding up? Well, if we were to make a ticker tape diagram, we see that in the first second, we move a shorter distance, and in the second and third second, as we go further on, the distance between markings becomes larger than it was initially. So we have an object here, a car, a little red car, that is accelerating. And what is its position versus time graph? Well, for any accelerating object, if it is accelerating smoothly, we get a nice smooth curve like what you see in the top left right here. A nice smooth curve is indicative of acceleration. And depending on if it's positive or negative acceleration, you might get a curve up or a curve down. If you have something that is velocity and acceleration in line or opposing, that also tells you about the direction of the curve. So the curve might look different for any type of motion, but for every acceleration graph, it will still have that same characteristic of being curved. If we were to look at velocity versus time, well, here we have a car that is speeding up. So over time, we have our velocity versus time graph increasing. And in fact, with this increase, we could figure out what the slope is, figure out the rise, meaning the change in velocity, and the run between any 2 points on this graph. And when we do the rise divided by the run, that tells us the slope of our graph. And that slope of this velocity versus time graph is the acceleration. So with this velocity versus time graph, we can figure out what the value of acceleration is, how quickly an object is accelerating. Now, I mentioned a second ago that depending on if your velocity and your acceleration are both positive, both negative, one's negative, one positive, you would get different shapes on your graph. And there's a couple that I want to revisit from last time that are going to be important for this free fall acceleration lab. And these two scenarios that I'm going to show you both have negative acceleration. And I'm showing you these two negative accelerations for a reason. And that's because when we talk about vertical motion, that is to say motion that occurs up and down, which is where free fall motion occurs. When we talk about our vertical motion, we generally say downward is negative. And free fall acceleration, the acceleration is always downward. Whenever you think about free fall acceleration, it is gravity causing that acceleration. Gravity always pulls downward, so the acceleration must be negative. So with free fall motion, we always say that the acceleration is negative. When we take a look at a object that has positive velocity and negative acceleration, we can see the position versus time graph curving, starting off with quite a steep slope and ending with a shallower slope. So we have a position versus time graph that still has a curve, but it is curving to be more downward over time. And this is our position versus time graph. Well, what is our velocity versus time graph? Velocity versus time graph here seems to have a negative slope. When you look at rise over run, you see that we're actually falling. And since we are falling, that gives us a negative slope. So our negative slope is indicating a negative acceleration. Like I said before, we will always get a negative acceleration when it comes to our free fall motion. Now, in the case of free fall motion, positive velocity would mean our object is moving upwards, and negative acceleration, well, that's again always going to be true for free fall motion. So you would see these same type of graphs if you were to analyze the motion of an object that has been tossed upwards. If it's tossed upwards, it has positive velocity and negative acceleration. And you'd get graphs very similar to what you see here. There's another case that we can look at, and that's negative velocity and negative acceleration. Here on our horizontal plane, we say negative is to the left, but again, in our vertical motion, negative would be downward. And when we have negative velocity and negative acceleration, our object is speeding upwards. And maybe this makes sense. You drop a ball, you allow free fall to take hold. It's going to speed up as it approaches the ground. What are the graphs going to look like? Well, you have a position versus time graph that this time, instead of starting out with a large slope and ending with a small slope, here our position versus time graph begins with a shallow slope. And as time progresses, the slope gets steeper and steeper. Again, still curved, but this time we have it curving downwards. Our velocity versus time again has a negative slope associated with it because it is a falling trend, and our acceleration came out to be a negative value. Again, this is something that will always be true for free fall motion. For free fall motion, you should always see your velocity versus time and your acceleration graphs looking similar to this. A downward slope on your velocity and your acceleration being flat, a flat line in the negative realm. But your position versus time graph might look different depending on if you see something that is moving upwards or you see something that is moving downwards. So some stuff to keep in mind. Now, when we talk about free fall motion, yes, we talk about this idea of acceleration. I mentioned over and over. What's interesting about free fall motion? What's interesting about free fall motion is that all objects that undergo free fall motion do so with the same exact acceleration. Now, in an ideal world, it would be exactly identical, but in the real world, we have some mitigating factors. Sometimes we have air resistance to deal with. Sometimes we have wind causing changes. So it's important to remember that, when we're talking about it for right now, where you're talking about, theoretically, in a perfect world, all objects would fall with the same acceleration. And what is that acceleration? Well, for a free-falling object, the acceleration near the Earth's surface is about 9.8 meters per second squared. And you'll notice here this acceleration. This acceleration has a negative sign. Why is that? That's because our objects always accelerate down towards the Earth. I've been studying physics for a while now, and I've never seen an object accelerate upwards when you drop it. So, pretty safe bet to say that the acceleration should always be negative here. So we have negative 9.8 meters per second squared. That is our acceleration. And if you remember, we can do some calculations here. We can make some predictions, right? Physics is all about making realistic predictions. And one of the things we can seek to understand is, how does its velocity look as time progresses? How does its velocity look as time progresses? Well, we can always calculate the velocity of an object if we knew its acceleration and how long it's been undergoing this acceleration. So we can take the acceleration, multiply it by how long it's been falling, and that should give us the velocity. So let's track it out. We're going to look at an object that's been falling for 5 seconds. In the first second, we can calculate its velocity by saying its velocity is acceleration multiplied by time, but here time is 0 seconds. So you take negative 9.8, multiply it by 0, and what you end up with? You end up with 0. For the next one, we say, well, how fast is it going at 1 second? We take that negative 9.8 value, we multiply it by 1, and you see that at 1 second, it is at 9.8 meters per second. And then in the next second, we say, well, what about at 2 seconds? How fast is it going? Plug it in, and you get 19.6 meters per second. And then at 3 seconds, you get 29.4 meters per second. And at 4 seconds, you get 39.2 meters per second. And then finally, 49 meters per second at the 5th second. So we're able to calculate out these different velocities. And then we say, okay, well, what does that look like on a graph, right? We always talk about graphs. What does that look like on a graph? We graph these out over time, and what you would see is a downward sloping velocity versus time graph. Downward sloping velocity versus time graph, we look at the initial condition, and our initial condition has us starting at that 0 point and going downwards, and the slope ends up being negative 9.8 meters per second squared. That is the acceleration due to gravity. We come over to the right-hand side of the screen and we create a ticker time tape type diagram for a freely falling object. We make a marking for every second that it's been falling. And we match those times with the speed that the ball is traveling at each of those seconds. So in that first moment, it's traveling at 0 meters per second. That's because we've just released it. We've just released it and we've allowed it to start falling. It hasn't had time to start accelerating yet. And over time, we see the speed increases, and it would increase up to that same 49 meters per second. Negative sign means downwards. So we say it progresses to that negative 49 meters per second downwards in that fifth second. So that tells us about velocity versus time, but that's only part of these quantities that we've been talking about, right? We've been talking about acceleration, velocity, time. What about its displacement? How far it's traveled? How far has the ball traveled over time? Well, we can calculate that out too. Displacement is calculated by taking 1/2 the acceleration and multiplying it by time squared. So with that same table, 0 through 5 seconds, let's figure out its displacement, that 0 second mark. 1/2 times negative 9.8 times 0 squared. Well, that's just going to be 0. What about at 1 second? We plug that in and we get negative 4.9. It'd be a good idea to pause and make sure that you are able to do all of these calculations. We would map out the second, plug in 2 seconds, and we get 19.6 meters downwards. We see that's quite a big jump. In that first second, it only traveled about 5 meters, and in the next, it makes it all the way to 20 meters. So it seems to be speeding up quite quickly. And in fact, in the third second, it gets to 44 meters downwards. Again, that negative sign means down. It's moved 44 meters downward. We keep going, and we have 78.4 meters downwards in that fourth second. Then we plug in for our fifth second, we would find 123 meters moved. We ask, okay, well, what does this look like? If we graph out the position versus time of the object, we see that we start out at some high up place. This is the top of the cliff where we start out. And then we start out moving quite slowly. Again, our velocity in that initial moment is quite slow. So we start off with a relatively shallow slope. And as time progresses, we start to move faster and faster, and we get this larger slope towards the end, indicating a faster moving object. And this is what our graphs for position or displacement over time would be. And we look back to our ticker tape sort of example where we map out each of the little dots. We take a look at this ticker tape and ask the question, well, where is the ball in each of those moments? And in each of those moments, we can map out where it is located by plugging in these values. We see in the first second traveled only 4.9 meters. And then after that, it traveled 19.6 meters. And then in the third second, it will have fallen to 44.1 meters. And then in the fourth second, it falls all the way down to 78.4. And then in the last second, it falls downwards and makes it all the way down 123 meters below the cliff. Those negative signs means that it's moved downwards. So that's the idea of free fall motion. Now, I made a claim earlier that free fall motion, well, it's the same for any object. And I'm going to try and justify that. Let me real quick. Stop my share. I'm going to switch over to this assignment. So we switch over to today's assignment. And in this assignment, we are specifically looking at free fall motion. And we're going to look at free fall motion as it pertains to objects that are flying up and down in this video that we're going to take a look at. I'm going to run it for a second, and we'll see several balls be thrown up. Now, these are all in slow motion. All of these balls are of different materials and have different masses. But what's interesting is that we see that they keep pace with one another. They all reach the highest points at about the same time. And we'll see that as they begin to fall, they all fall downwards in identical paths. So we have our balls all falling downwards and identical timings, moving the same amount of distance in the same amount of time. And what does that mean? Well, that seems to indicate here that they do all share the same motional quantities. They had the same positions and displacements. If we look at their vertical positions, yeah, they were spaced out horizontally. But if we look at their vertical positions, they all had about the same vertical position. They all seem to move at about the same speed. And since they shared position and speed, it must be the case that they shared acceleration too. And as you go throughout the lab, you will eventually get to the point where you are asked the question of what is the acceleration of these objects. And once you have that answer, you'll see that that number, well, it should look pretty familiar to you. As far as the analysis of this lab goes, it's very similar to what you did last week. So take your time, take your measurements one at a time, and it should go relatively quickly. It should be very familiar to last week. All right, I'm gonna end the recording here in a second, but I just want to remind you that, as always, if you have any questions, don't hesitate to ask them. I am happy to get back to you as soon as I can. Usually give me like 24 hours if it's a weekday to get back to you. But again, if you have any questions or any concerns, please always feel free to reach out to me. Okay. I will see you all next week and have a wonderful day.